Great.
So welcome back, everybody, and for this last session of the day. And our speaker now is Macarena Lagos from Kavli Institute of Cosmological Physics in Chicago, and she will speak about testing cosmology with gravitational waves. So the stage is yours, Macarena.
Great, thank you. Yeah, so as my title suggests, I would like to tell you about how we can test cosmology, in particular test the possible physics beyond the LCDM concordance cosmological model, and focusing particularly on using gravitational waves for this task. So before I get into all the details, let me just start by summarizing why I think it is important that we test cosmology and the LCDM model further. So the LCDM model assumes these to be the universe constituents, where you can explicitly say that 95% of the total energy content of the universe is in the form of dark matter and dark energy. These are components whose nature and exact behaviors are actually unknown. So certainly we have a lot of work to do as theorists to try to understand better the behavior of these components. Now, from an observational point of view, the LCDM model is doing overall very well. However, now that we are getting more and more data and more precise constraints on our cosmological parameters, some tensions have started to arise. So here you see, for example, these figures showing the possible values constrained from different data sets on the current Hubble rate H0. And there you see that there are two classes of constraints or observations, the red and the blue ones. So the red ones come from local observations of the nearby universe, and the blue ones come from kind of cosmological observations that usually make assumptions about the entire history of the universe. And these two classes of constraints are in tension between each other. And well, the particular amount of tension can be quantified between 4 and even 6 sigma, depending on the particular data set that you pick. But the point is that that it could be possible that the assumptions that we are making about cosmology are affecting and biasing the constraints that we find for our cosmological parameters. So we do need to test further our cosmology. So with this in mind, in the future, we will have certainly a lot of data from the usual or standard electromagnetic probes for cosmology. That means the cosmic microwave background and galaxy surveys. There will be a number of telescopes that will become online in the next few years that will certainly contribute for that task. But here I want to tell you how we can exploit now this new side that we can use as a complementary or independent probe that are gravitational waves. So we already have some detections from LIGO and Virgo. CAGRA has joined the network, and hopefully in the future we will have more detections from other, third generation gravitational wave detectors in the ground and in the space also. And overall, actually, we will detect gravitational waves from different sources at very high redshifts, so even redshift 10. So these will certainly allow us to test cosmology up to that redshift. So when I say that we want to test a cosmology or the LCDM model, then we actually need something to compare to see whether the data is going to prefer the LCDM model or a possible alternative. So in the past decade or so, all these modified gravity models have been studied, and mostly people have worked on analyzing a given models one by one, and it turns out that hasn't been super efficient, because at the end of the day, many of them either don't fit very well the data, or they distinguishable to LCDM or fine-tuned, or they have instabilities and so on. So here, what we try to do to describe possible modifications to the LCDM model is to use a more agnostic approach. In the previous talk, the speaker mentioned this effective field theory of inflation, and we actually do take a similar approach based on effective field theory, but now to study the late universe. So mainly in what the mathematical procedures that I will be mentioning are very generic, but I will be having in the back of my mind that they are describing the late universe and possible modifications to the LCDM model based on modifications to the behavior of dark energy. So beyond the LCDM model, you could have that these new modified gravity or new cosmological models change, for example, the expansion history of the universe and or the evolution of inhomogeneities, like large-scale structures. And it turns out that many models, specific models that people have studied, do predict an expansion history very similar to the LCDM model. Sometimes it looks exactly the same. So in my focus, I will be focusing on trying to see how different models predict the evolution of inhomogeneities, because even though they may predict the same expansion history, they could still highly differ on how inhomogeneities evolve. So we're gonna take the effective field theory approach, in which basically we're going to work at the level of the action, and we're going to write down the action that describes the evolution of these inhomogeneities that are going to be described by just linear perturbations around a cosmological background. And we're going to add some free parameters in there for each one of the possible terms that could be present in that action. And the hope is that we constrain in the future those free parameters. Regarding the background, the expansion history, we're going to be completely agnostic about what that is. We usually are just going to assume that it evolves in the right way that fits the data, and just focus on trying to parameterize the different possible evolutions of these cosmological perturbations. So the procedure would be as follows. First, you fix your given background. So you're going to say, I have a cosmological background that is completely homogeneous and isotropic. And you could change that assumption if you want, but this is what we do. Then you write down all the possible quadratic terms for linear perturbations for all the fields that could be present in your gravity theory or in your cosmology model. So in my case, I will assume that I don't know how the metric behaves, and I don't know how, and that there is one additional field that actually will correspond to the dark energy field. So the cosmological constant now is promoted to be a field in these modified cosmologies. And I don't know how this field behaves and also how it interacts with the metric. So we write down all the possible interactions that the metric and this extra field could have. And as I said, we're going to add a free coefficient in front of each one of these possible interaction terms. And in order to have a finite number of interactions, you do need to make some assumptions. So for example, we cut the number of interactions up to a maximum of derivatives. So this is, again, effective field theory, where your model is valid only at low energies, and you apply that for cosmology. And in our case, we also include the assumption that these models will have an additional gauge symmetry, simply because that's very common. Most of the theories that we study in the literature do exhibit some kind of gauge symmetry. So we also, at least in our procedure, we incorporate in our method the possibility of having certain symmetries. So the idea is that these parameterized cosmologies will encompass the possible cosmological evolutions predicted by a number of gravity theories. So now, when I say gravity theories, I mean a non-linear gravitational theory. But in my case, I am only describing cosmological models that are for linear perturbations. So with these free parameters, the idea is that if they take a specific form or a specific values, then they will correspond to the cosmological evolution of certain specific gravity theories. I will give some examples later. The idea is that all these free parameters are going to, in principle, affect observations of inhomogeneities that will affect the cosmic macro background, large-scale structure observations, as well as gravitational waves. And I will show you later specifically how gravitational waves will change. And finally, the specific examples that I will be mentioning all have the same properties. In all of the cases, I will assume that my cosmology model has this gauge symmetry, as I said before, that it is diffeomorphism invariance in that case, that all the equations have at most second order derivatives. I will also assume that these cosmologies differ from lambda CDM or from general relativity by having one extra additional field that, as I say, in the back of my mind, I'm going to be thinking that this is a field that would correspond to dark energy. And also, for simplicity, we do not change the way the rest of the matter components in the universe, including dark matter, are coupled to the metric. So our only ignorance in this case is how the metric interacts with dark energy, and those interactions are going to have these free parameters. So let me just give you some examples. If you say, what if this additional field in this cosmology model is a scalar field? And if you assume that it is diffeomorphism invariant and has second order derivative equations of motion, you get that there will be 4 additional parameters in this extended or modified cosmological model compared to lambda CDM. So these 4 parameters are given these names: alpha m, alpha k, alpha t, alpha b. The names are given according to what they actually do. So each one of these parameters will modify your observations in different ways. Here for alpha m, I write in parentheses this capital M because later you will see a free parameter called capital M that will actually be related to alpha m. So either m or alpha m is the free parameter. So just to give you an example of what these parameters do, alpha t, for example, is called the tensor speed excess, and it changes the propagation speed of gravitational waves. In lambda CDM, they propagate at the speed of light, but in this, if now you have an additional scalar field in your gravity theory, that in my case, I assume it to be the dark energy field, then the propagation speed could change. Also, alpha m will be important, and this m, capital M, is called the effective Planck mass. That will actually also affect, as you will see later, the propagation of gravitational waves. So I don't want to write you like the full action that is valid for all kind of observations. You just have to imagine that we have a cosmological model that has the lambda CDM parameters plus this extra 4. Now you could complicate the situation a little bit more and say, what if my additional field in my gravity model was a vector field instead of a scalar field? And again, under diffeomorphism invariance and second order derivative equations of motion, you get that you would have to extend lambda CDM to include 8 additional parameters. So you have more simply because a vector field propagates more degrees of freedom than the scalar field. And again, we give them all these names, alpha k, alpha t, according to what they do. And one more case that we actually analyzed was the case where you had an additional field that was a tensor, so a spin 2 field. So in this case, you're going to have 2 kind of metric, 2 spin 2 fields, the actual metric, and this additional tensor dark energy field. And in this case, you in principle, actually, if you're completely agnostic about how these 2 tensor fields could interact, you get a lot of parameters, but we made some simplifying assumptions to reduce the number of parameters and get only 4. So in this case, These describe models where the two tensors, so the actual metric and this tensor dark energy field, interact only through non-derivative terms. So as I said, these cosmological models and free parameters describe the cosmological models that come from different nonlinear gravity theories. So for example, in the scalar case, these describe all the possible cosmologies coming from Horndeski theories. In the vector case, that would correspond to generalized Broca theories. And in the tensor case, here we describe the cosmologies that come from massive by gravity. So this is just to connect these kind of effective field theory cosmology models to actual nonlinear gravity theories that are known in the literature. So all these alpha parameters have common properties. The idea is that we recover general relativity or lambda CDM when all the alphas vanish. So the hope is to test, use your data, your observations to see whether they prefer a non-zero value for these alpha parameters or not. They are all dimensionless parameters that I call parameters, but they're actually functions of time. So in this effective field theory approach, the first step was to assume that you had a given background and perturbations around that background. And all these parameters will inherit all the properties of the background. So if you consider a cosmological and time evolving background, then these parameters will be functions of time. So that complicates things because you usually will have to make an assumption about how they actually evolve to get a meaningful constraint for them. And again, I just emphasize that all these parameters will modify the evolution of inhomogeneities in the universe. All of them will actually affect CMB and large scale structure, and not all of them will affect gravitational waves. Nevertheless, for the few parameters that do affect gravitational waves, you can use gravitational wave data and observations to get independent constraints. So here I'm going to show you specifically what is the parameterized action, cosmological action that we obtain that concerns tensor perturbations. So this is the action that you obtain for the case of a scalar and vector dark energy, the first two cases that I mentioned. Here you have first HA, this is your field, it represents the gravitational wave amplitude. And A is just a subscript that is not for amplitude, it's a subscript for the two possible polarizations that your spin 2 metric could have. And under the assumptions that we made, actually the two polarizations evolve in the same way. So this is the same action for any value of A for any polarization. And here you have just prime is a time derivative. Here you have spatial derivatives. And this action is telling you how gravitational waves propagate on a cosmological background. So this is relevant for when you're studying waves that travel over cosmological distances and you want to see how they evolve in time. So here you have the scale factor just of the expansion of the universe. And now we're going to see the first modification that appears beyond lambda CDM, which is the presence of this capital M that I mentioned before, the effective Planck mass. In lambda CDM, here you have this capital M has a very specific form, which is a constant, and it takes a specific value, which is the Planck mass. But generically, if you have this additional dark energy field that has non-trivial interactions with gravity, then this coefficient here is not necessarily a constant Planck mass. It could be an effective new mass term that could even evolve in time, depending on how dark energy evolves in time. So this is the first modification. And now the second one is the tensor speed excess, is alpha t that I also mentioned before. This alpha t changes the propagation speed of gravitational waves. When alpha t vanishes, then waves propagate at the speed of light, but then for any non-zero value of alpha t, then there is a non-zero deviation from the speed of light.
Sorry, Macarena.
Yes.
Chuncha as a question for you.
Sure. Can we absorb this time dependence of Planck mass into the redefinition of scale factor? It looks like you have m squared and a squared.
Yes, you could. So this is related to the issue of the Einstein frame versus the Jordan frame, typically that people discuss in modified gravity, that conformal factors could be reabsorbed into redefinitions of the metric and so on. So you could do that. I mean, at the end of the day, all the observations are going to be the same. You would have to interpret things differently. But in principle, you could do that. But here, I usually assume that we are in the so-called Jordan frame, because I think it's easier to interpret things in that frame. H is the actual metric that couples minimally the rest of the matter components. So I think it's usually easier to interpret things in this frame. You could reabsorb this in A and reinterpret things. Yes.
Okay, thank you.
Also, later I will show the equation of motion that comes from this action. I mean, just varying this action, and there it will also be clear that m kind of changes the effective Hubble rate that these gravitational waves feel, which is equivalent to related to your question that you could interpret this m as a change in your conformal factor. Okay, so these two are the simplest modifications that you could expect to have in the gravitational wave sector, that, as I said up here, when you have an additional field that could be a scalar or a vector field. Now, you could have certainly more complicated situations. So when you have the tensor dark energy field, so these are tensor theories or biometric theories, and this is, for example, the action that you find. So you have, in the first line, you have similar kinetic terms to the one that I showed you before for the metric HA. But now this metric, these gravitational waves, will be coupled to the waves of the second spin 2 field, the second tensor or metric field that we call H2A. Now, because of the simplifying assumptions that I mentioned before, here the interactions between the actual metric H and the second spin 2 field is only through non-derivative terms. So these are kind of mass interactions. And here the modifications, how these will modify your observations, is much more complicated. Some authors have studied, for example, that these kind of mass mixing or mass interactions will lead to oscillations of your gravitational waves between H and H2A, similar to, it's analogous to neutrino oscillations, because this biometric action actually describes the propagation of a massive with a massless spin 2 field, and they kind of oscillate among them. So well, you certainly could have many more complicated modifications, but just to be concrete, in the rest of the talk, I will discuss how we can constrain, in the simplest case, this alpha t and this effective Planck mass. And as I said, all the rest of the alpha parameters that I showed you before that do not affect gravitational waves can be constrained, and for some models have been constrained with CMB and large scale structure observations. Okay, so now let's talk about gravitational waves. So these gravitational waves are emitted in this very strong field environment, and after they are emitted, they start propagating towards us over cosmological distances. And that action that I showed you describes how these waves are going to propagate, and that is mainly when we are going to test cosmology. Now, more specifically, I will be talking about how to exploit multi-messengers from these kind of sources. So when you have these gravitational wave emissions, sometimes the sources can also emit light. And if you're lucky enough, you can detect both. So in this picture, for example, we have a binary system of compact objects. And they could be neutron stars, but they could also be black holes, supermassive black holes, for example, that are in a gas-rich environment that also emits light. But the point is that if you get both signals, these multi-messengers, then you can exploit the differences and between these two signals to test, well, your cosmology or to test gravity. So the most famous case is the neutron star, the only binary neutron star confirmed detected by LIGO, GW170817. So in this case, there was an electromagnetic counterpart emitted at the moment of the merger and afterwards. In this figure, you see at the top the gamma ray burst that was emitted from this binary neutron star when they merged. So here you have the signal as a function of time. So the x-axis is time, and it peaks here at a certain time that you typically associate to the time of the merger. And then at the bottom, we have the gravitational wave signal, but now in frequency space. So we have frequency as a function of time. Here, this shows the gravitational wave frequency evolution. And here, t equals 0 by definition is when the gravitational wave signal and the frequency peaks that again we associate to the merger. So as I said, we want to kind of complement or exploit differences between these two signals, and the simplest comparison that you could do is to compare their arrival times. So in this case, the electromagnetic signal arrived about 2 seconds after the gravitational wave signal, and then you could ask, okay, what if that difference was due to the fact that maybe gravitational waves propagate faster than light? So you could set a bound on how fast gravitational waves could propagate, and that bounds the value of this parameter alpha t. So using that information together with the fact that you knew how far the source was in this case at about 40 megaparsecs away, you end up constraining alpha t to be smaller than 10 to the minus 15. So recall that alpha t is this dimensionless parameter. And it basically tells you what is the difference between the speeds, the fractional difference between light and gravitational wave speeds. So this is the bound that was found and quoted by the LIGO-Virgo collaboration, and it is actually very tight. We didn't have at that time such a strong bounds and constraining upper bounds on the propagation speed of gravitational waves. And because of this, in this work, for example, we showed that many dark-specific gravity models are going to be disfavored because they typically do predict that alpha t is non-zero, and they will usually not satisfy this bound. So because of this, nowadays, people usually assume that alpha t probably is 0 and gravitational waves propagate at the speed of light. So let's continue working under that assumption and study how now we can constrain also with these multi-messenger signals the other second modification that was this effective Planck mass. So here's where these names, standard SIRENS, come into place. So when we have this binary system of compact objects, they have different stages. So at the beginning, they are far away, but in spiraling into each other, losing energy in the form of gravitational waves and getting closer until they eventually merge. And after they merge, they form a new single compact object that stabilizes, also emitting additional gravitational waves. So we have these 3 stages, and it turns out that at least during the inspiral, or at the beginning of the inspiral, the gravitational wave emission is rather universal. is very standard. It is understood from first principles from general relativity, and it is kind of universal in the sense that it doesn't really depend on what the specific objects are, because they are far enough that you just consider them to be just point masses, and it doesn't matter if they're black holes or neutron stars. The gravitational wave emission will look pretty much the same. So as a first order approximation, actually, the frequency, the gravitational wave frequency evolution in time satisfies this relation. So by looking at the waveform, at basically what is the frequency detected and how it evolves in time, you can constrain this parameter of the binary system that is called, well, the redshifted chirp mass. But it turns out that this is kind of the main parameter that determines the properties of your binary system at the early stages of the inspiral. So just by looking at the frequency evolution, you constrain this parameter, and then you look at the entire waveform. So you look at, sorry, an entire wave signal, you look at the strain. So the strain H is just the particular way in which the gravitational wave interacts with your given detector, and its form, its specific form, generic form is also known, as I said, from general relativity, and the main free parameter is this chirp mass that will be fixed. Then you have here the frequency. Here you have just the phase of the gravitational wave signal. Here you have f of angles. This is just a function, again, that encodes the information of how the gravitational waves interacts with the detector. So it is a function of the position of the source and also the inclination of the binary. But in principle, it is something fixed for a fixed source. And then we have this distance here. So the amplitude of the strain actually decays as 1 over this distance that we call the gravitational wave luminosity distance, and basically tells you how far the source is by taking into account the expansion of the universe. And this is the main quantity that encodes cosmological information from which we can extract, well, cosmological constraints. So the idea is that using just only the gravitational wave signal, you get constraints on this chirp mass, m. And by looking at the amplitude of the strain, and you already have constraints on the chirp mass, then you can get constraints on the gravitational wave luminosity distance. So just from the gravitational wave sector, you get constraints on this distance. So then how do we get cosmological constraints, or I mean constraints on cosmological parameters from this distance? Well, it turns out that in LCDM, this distance is equal to the luminosity distance, and I said it encodes information about the expansion history of the universe, and particularly for LIGO, I will be focusing on LIGO, low redshift sources. You can approximate this just by the usual Hubble law. So this is the redshift of the source and the current Hubble rate. So here you explicitly see how in this distance and in the amplitude of the strain, the gravitational wave signal, cosmological parameters are starting to appear. Now, if dark energy is not this cosmological constant, and instead you have an additional field in your cosmology, actually this gravitational wave distance is not exactly equal to the luminosity distance. They differ by this factor that corresponds to the effective Planck mass m that I mentioned before at the moment of detection. So this is redshift equal to 0 today. And at the bottom, we have m at the moment of emission. And just as a check, in LCDM, I said this effective Planck mass is just a constant. It is the Planck mass, and this ratio is equal to 1. So you recover that the gravitational wave distance is the luminosity distance. But in general, in these dynamical dark energy models or modified LCDM models, m could evolve in time. So the gravitational wave distance actually will encode information about how m is evolving in time, and therefore will encode information about the behavior of dark energy and how dark energy interacts with gravity. So the reason why you get this ratio here is because if you look at the equation of motion that came from the action that I showed you before, it's going to look like this. So here you have h, just second time derivatives. Here you have k, is the wave number, and I have assumed that these waves propagate at the speed of light already. And here you have a kind of friction term that is proportional to first derivative of h, of the gravitational wave amplitude. And you always, even in LCDM, you get a term like this, proportional to h, which is the Hubble rate. And this is just telling you that the amplitude of gravitational waves feel this additional friction and decay extra when they propagate over cosmological distances, simply because the space is expanding. But now that you have these time varying affecting Planck mass, actually you will have an additional contribution here to the friction term, that is this alpha m, that is given by this formula. So alpha m is proportional to the time derivative of m. So if m is a constant, alpha m vanishes, and you recover the LCDM model where only h, the actual Hubble friction, affects the amplitude of gravitational waves. But if m is varying in time, then you will have an additional friction. So that means gravitational waves will decay more or less with respect to LCDM, depending on how dark energy interacts with gravity. And this will translate into a different amplitude of the strain, and therefore a different amount of gravitational wave distance. So now let's try to get cosmological constraints from this gravitational wave distance. So I recall that I said that all these alpha parameters do have a time evolution. I mean, they could have a time evolution. They could also be constants if you want. But normally, this is a very common parameterization for the time evolution, because if you are motivated, you motivate these modifications through dark energy, then usually it is natural to assume that alpha m would also evolve in the same time scales as your dark energy field evolves at the background level. So this is an assumption. We're going to assume for simplicity that alpha m is equal to Cm, where Cm is an actual constant parameter. It is the one that we are going to try to constrain, times a given time evolution that in this case will be proportional to the fractional energy density of dark energy. So whenever dark energy is relevant at the background level, then alpha m will be, relatively large. Whenever dark energy becomes irrelevant at the background level, then alpha m will be close to 0. Nevertheless, we did an analysis for LIGO. LIGO is only sensitive to low redshift sources for binary neutron stars, which is what we focus on. And we don't think that this time evolution really changes that much the constraints that we will find for CM that I will quote later. So the point is that now under this assumption, this parameterization or gravitation wave distance generically for low redshift sources will depend on the redshift on H0. So these are because of the just Hubble law. And then we'll have this additional dependence on CM because it has this extra ratio of masses. Now, as I said, just from the gravitation wave data alone, you get constraints on the distance. And on the right-hand side, if you are absolutely agnostic about your cosmology, in principle, you don't know anything. You don't know the redshift, you don't know H0 if you don't want to use other cosmological probes, you don't know CM. So that's the reason why we do need something extra if we want to do cosmology with gravitational waves. And that extra piece of information could correspond to the electromagnetic counterpart, because the electromagnetic counterpart could allow you to localize your source and identify the host galaxy of this event and get the redshift. Now, if you do know the redshift, then in principle, you could set constraints on both these H0 and CM. And this is what we do. So we said, well, with one single event, like 170817, really we do not get, very powerful or competitive constraints compared to, current standard cosmological probes. So let's look at the future. What if we had 100 binary neutron star detections where we do get the redshift with an electromagnetic counterpart? So we get the redshift pretty well. That's what we assume. Then with this number of events, we kind of simulate this population of 100 events, and we constrain CM and H naught. This is kind of the figure for the posterior joint probability for these two parameters. And I mean, qualitatively, I only want you to get the fact that the CM and H naught are largely degenerate here. Now, more quantitatively, the main results are that with 100 events, you could constrain H naught to 1 to 2% precision. So this becomes comparable to the current constraints on H naught that I actually mentioned during my introduction. The difference is that these constraints are completely new, are completely independent from the rest of the other H naught constraints. The constraint on this parameter CM, the uncertainties actually on the constraints on this parameter CM should be of order 1 with 100 events. And well, what does that mean? Well, there are dark energy models that could predict a CM of order 1. So, but not all of them. Some of them could predict a much smaller CM that you wouldn't be able to distinguish from lambda CDM with 100 events with LIGO. But at least some of these models you should be able to test. And now regarding this degeneracy that I told you, that I showed you in the picture, what is the consequence of that large degeneracy? The consequence is that if you assume something wrong about CM, for example, you assume that CM is equal to 0 because you like lambda CDM, but actually CM was not 0 and was something close to order 1. In that case, you will bias your constraint on H naught by 3 to 4 sigma. So this degeneracy and this bias example is just emphasizing the importance of testing extensions of lambda CDM in general to make sure that the fundamental assumptions that we make about our universe are not biasing and affecting the constraints. And that's especially important for sensitive parameters like H naught, that we really need to make sure that the constraints that we find are robust. So just before I finish, a comment on this redshift thing. In this kind of simulation of populations and in these quotes that I mentioned for how precise the constraints could be, we did assume that we had an electromagnetic counterpart, in the sense that we assumed that we got the exact value of the redshift. We got just one redshift associated to each event. So that you can do if you get electromagnetic counterparts, but now people are questioning whether that's actually realistic or not, to assume that we will always get an electromagnetic counterpart. So there are alternative ways in which you could perform these same tests, but of course the precision of your constraints will be different, but the procedure is similar. So one is to use your gravitational wave data and the localization that just with the gravitational waves detectors you get. So you get a localization in the sky for the sources, and there you basically look at galaxy catalogs and to all the galaxies that could be in the localization volume, and then you assign a probability for each galaxy being the host. And therefore you have like a number of redshifts that could be possibly associated to one event. So then you can do a statistical analysis if you have many events, but in this case, well, because you don't know the redshift exactly, you will need more events than 100 to reach the same 1% constraint. Also, there are other effects, like the galaxy catalog may be incomplete, so that adds this extra uncertainty. So these constraints for 100, for example, gravitation wave events if you do this statistical procedure, the constraints on H0 are going to get degraded by a considerable amount, by a factor of 5 to even 10, with 100 events, but doing it statistically. Now, other methods proposed and studied in the literature correspond to what if the population of your sources had certain features in the mass distribution. So the importance of this is that the redshift is degenerate with the mass of the binary system. So that's why you have no information about the redshift, because you have no a priori information about the mass. But if you do know something about the mass, for example, that for binary neutron stars, the masses have a certain distribution for the possible masses peaked around 1.4 solar masses, or if you think that solar mass black holes have gaps, so have like an upper or lower limit, then you could use that information to again set bounds and constraints on this redshift, and again you could do a statistical procedure. But this mass features procedure just depend on very important physical assumptions that in principle you should test first, like these gaps and these mass distributions of neutron stars. But the main message is that you could potentially do the same procedure and obtain the same cosmological tests, but without getting exactly an electromagnetic counterpart. So just to summarize, I first discussed that we can use an effective field theory approach to describe cosmological models beyond the LCDM model, and I mentioned 3 different examples where you could apply this effective field theory approach. One that describes scalar tensor theories, the other one vector tensors, and the third one tensor biometric theories. I showed you that in the scalar and vector cases, those are the simplest cases in terms of how they affect gravitational waves, and they introduce 2 new kind of physical effects. One is a change in the propagation speed, and the other one is a change in the friction that gravitational waves feel when they propagate over large distances. I mentioned that with multi-messengers, so with gravitational and electromagnetic signals, you could measure pretty well just with one single event. Looking at time delays, you can measure pretty well the gravitational wave speed. With these same multi-messenger events, you can test also your expansion history of the universe. I mentioned the case of constraint on H0 for these low redshift sources of LIGO. And you could also constrain the behavior of dark energy through this parameter CM that I introduced. You could reach a constraint on H0 using 100 events that is close to the current constraint on H0 in terms of precision. I also try to get across this warning that there could be effects degenerate with H0 that could bias your constraint on H0, so they're important to test. And finally, I mean, just an additional comment to discuss for the future. All the things that I mentioned concern the propagation of gravitational waves on a perfectly homogeneous anisotropic universe, but we know that that's just an approximation. We know that there are inhomogeneities, and they could be relevant, especially for 3rd-generation gravitational wave detectors like LISA or Einstein telescope, also for pulsar timing arrays. And these lensing effects could actually change everything about your gravitational wave signal. The simplest thing is that they could actually introduce, for example, a magnification and change what you would think is the gravitational wave distance and what you would use to get cosmological constraints. So it's important to actually be very careful about whether these events are lensed or not when you are getting cosmological constraints. And actually, they could change all their properties about your gravitational waves, not just the overall amplitude. They could also change the polarization. It could change the time delay that between light and gravitational waves, and overall just the phase evolution of your waves. So these are things that may look like relevant very far away in the future, but in order to really understand the power and how we can really use gravitational waves as a complementary probe for cosmology, we do need to develop a case study of all these different effects today as soon as possible. With this, I finish this talk, and thank you very much for listening.
Thank you, Macarena. So we have one question from Gian Massimo.
Yes, hello. Thanks for the nice talk. I was wondering about the last 2 points that you made. So there is degeneracy between H0 and D and dark energy and lensing. Can lensing provide degeneracies also that mix up effects of dark energy with effects of lambda CDM? And do you know whether there are effects of dark energy that are not degenerate with lensing?
So to the first question, lensing, yes, would be degenerate with these dark energy effects, because as I said, lensing, if it changes the amplitude of your gravitational wave signal through magnification or demagnification, it will affect what you constrain for this gravitational wave distance. And from that distance, it's really where you get constraints on dark energy, on H0, and omega matter if you go to higher redshifts. So yeah, you do expect it to be degenerate. Now, one difference is that lensing would only affect some of the sources, whereas dark energy is this fundamental property of your universe that should affect all the sources. So possibly that could help you. But you really, I mean, a question actually open nowadays is, how do you actually know if your event was lensed or not? That's the first question. And there's not a clear answer for that yet. Now, the other thing of that concerns polarization and time delays and waveform is that lensing could, gravitational waves could have a rather large wavelength compared to astrophysical sizes. So actually, gravitational waves, when they propagate and they encounter these lenses or inhomogeneities, they could feel interference effects. So they wouldn't propagate just like light in geometric optics, where the signal just bends around a given path and that's it. These gravitational waves could suffer from interference effects due to their very large wavelengths compared to the lenses. And that, I mean, we have actually studied that, for example, that could change the time delay that you could see between light and gravitational waves, just because light propagates according to geometric optics and gravitational waves don't. And that could be degenerate also with other effects of modified gravity, that there is actually a genuine change in the propagation speed of gravity. So, so I think there are a lot of degeneracies. So the main question to answer, I think, for now is, how do we even know that these events are lensed? I don't have an answer for that now.
Okay, thanks.
We have time for a second question. Someone raised his hand, I see.
Hi, if I may ask a question. If this additional cosmological terms are not zero, I think in principle it should also modify the gravitational waveform, right? So because it can modify the propagation equation of the gravitational wave. Is that true? And if that is true, then you can also compare the waveform with the data, either with EM counterpart or without EM counterpart. That will also give some constraints on these cosmological terms as well.
Right. So, I'm going to give two answers. One is regarding the specific modifications that I consider. So if you have a non-zero alpha t and a non-zero alpha m or a time-varying effective Planck mass, you do not change the waveform. As I said, I mean, and the main reason is that because these parameters only depend on time, on the cosmological evolution, and don't depend on the frequency. So if alpha t is non-zero, the waveform is exactly the same, but you just have a different arrival time because it propagates at a different speed, and the effective Planck mass, if it has a time evolution, then it just changes the kind of total amplitude of your signal, but not the waveform. You could now consider more complicated extensions of the LCDM model, like this bimetric, or maybe the same one that I use for alpha t and m, but introduce the possibility that these parameters could have a frequency evolution. Then in that case, there will be a change in the waveform, and you could constrain those kind of situations much better in general, because the waveform, well, it has a very specific form and people measure the phase evolution pretty well.
Okay, so we have no further questions. So let's thank Macarena again